Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to error analysis. So previously we discussed basic concepts related to error analysis in unity feedback systems, and we discussed some questions related to it. So in this video we are going to discuss an important concept, which is basically the relationship between type of a system and steady state error. Okay, so this will be particularly helpful when it comes to MCQs, multiple choice questions, or objective type questions where you need to save time. So deliberately I introduced this concept right now. Otherwise you would have only gone for the shortcut approach. So that's why I'm discussing it right now after you have followed the usual process to get the steady state error for unity feedback systems, the step-by-step method. This is the shortcut method. So we know that the type of a system is basically the number of poles of the system at origin. That is called as type of a system. So let us say we have a system, unity feedback system, with open loop transfer function, which is given as this, let's say. So here this determines the type of the system, this S, only S here, single S. So here if it is S to the power 0, which means 1, then it is a type 0 system. Okay, so here if this is only S to the power 1, then it is a type 1 system, which means it has one pole at origin. Okay, so this is a type 1 system. This is type 0 because basically S to the power 0 means 1, so means no pole at origin. Another case is here, S plus A, S square, S plus B into S plus C. So here it is a type 2 system because S square represents 2 pole at origin. So similarly, if there are nth pole, n number of poles at origin, which is represented by S to the power n, S plus B into S plus C, then this is a type n system. So we are particularly interested in type 0, type 1 and type 2 system in this discussion related to steady state error. So suppose first we pick the type 0 system. Okay, we are considering the type 0 system. So this is represented by this transfer function. Let's say k into S plus A, S plus B into S plus C. So here we have to find out the error coefficients. So first we'll determine the let's say position error constant Kp, which is equal to limit S tends to 0 GS, which is equal to limit s tends to 0 k into s plus a, s plus b, s plus c. So it is basically k into 0 plus a, 0 plus b, 0 plus c. So that is equal to ka by bc. So if it is a unit step input, let us consider that the system is supplied with a unit step input. In that case, the steady state error because of the unit step input will be 1 by 1 plus kp, where kp is equal to this ka by bc. This is for step input. Okay, then we'll determine the velocity error coefficient kv is equal to limit s tends to 0 s gs. So that is equal to limit s tends to 0 s into k into s plus a by s plus b into s plus c. So here no need to do anything. If there is s in the numerator and limit s tends to 0 we have to evaluate, means there will be 0 in the numerator. So when 0 comes in the numerator, the result will be 0. No matter what the other values are, the result will be 0. So in that case, if we are considering a unit ramp input being applied to the system and we have the velocity error constant equals to 0, then the steady state error because of the unit ramp input is equal to 1 by kV is equal to 1 by 0, which is equal to infinity. Then let us determine the acceleration error coefficient, which is equal to limit s tends to 0 s square gs. Same result, it will be 0. Why? Because there will be 0 in the numerator by s plus b into s plus c. So when this becomes 0, s square, and all we substitute all the s with 0, it doesn't matter. When this becomes 0, the result will be 0. So here the steady state error, if we consider a unit parabolic input being applied, so in that case it is 1 by ka is equal to 1 by 0, which is equal to infinity. So here if we try to interpret the results for a type 0 system, only for step input application we have a finite value, I mean a non-zero value, which is neither 0 or infinity. This kind of a result, numerical result we are getting. And for the remaining, that is for ramp and parabolic, the result is infinity. Okay, so this is type 0 system. Next, let us consider type 1 system. Okay, so we will be considering a type 1 system. So here let us consider a type 1 system, which means one pole at origin. So let us consider the open loop transfer function expressed as k into s plus a, s one pole at origin, s plus p, s plus c. Okay, so type 1 system means there should be one pole at origin. No matter how many zeros or poles are there, it doesn't matter, but there should be one pole at origin. Okay, so this is the type 1 system we have considered. So first we'll determine the position error coefficient Kp, which is equal to limit s tends to 0 gs, which is equal to limit s tends to 0 k into s plus a by s into s plus b into s plus c. So here please pay attention. Here when we substitute in the denominator this single s as 0, no matter what the other values we substitute or the values of the other poles and zeros there are, 0 when comes in the denominator, the result will always be equal to infinity. When this we substitute with 0, something by 0, it will always be equal to infinity, because 0 will get multiplied with all the other factors in the denominator and the result will be 0. Something by 0 is equal to infinity. So here position error constant is equal to infinity. Let us consider that a unit step input is being applied. So the steady state error is equal to 1 by 1 plus kp, which is equal to 1 by 1 plus infinity, which is equal to 1 by infinity, which is equal to 0. Then this is for step input. Then let us consider a ramp input being applied. So for that we have to determine the velocity error coefficient, which is equal to limit s tends to 0 sgs. Okay, so here it is limit s tends to 0 s multiplied with k into s plus a by s into s plus b into s plus c. SS gets cancelled in both the numerator and denominator. When we substitute it with 0, it becomes k into 0 plus a, which is equal to a. Then in the denominator s plus b we substitute, it will be 0 plus b, which means only b, 0 plus c, which is equal to c. So it is ka by bc, a finite value we are getting, neither 0 or infinity. So in that case, the steady state error for a unit ramp input, it will be equal to 1 by kV, which is equal to this, where kV is equal to this. So it will be bc by ka, but regardless of that, it is we are getting a finite result, neither 0 or infinity. Next, we will consider a parabolic input. For that we have to determine the acceleration error coefficient, which is equal to limit s tends to 0 s square gs, which is equal to limit s tends to 0 s square multiplied with gs k into s plus a s into s plus b into s plus c. So here in the numerator it becomes s. Again, when we substitute s with 0 in the numerator, we will have 0 being multiplied with whatever other values there are. So in the numerator there will be 0. So when in the numerator the net result is 0, means the total value will become 0. Okay, so here k is equal to 0. So steady state error for a unit parabolic input will be equal to 1 by ka, which is equal to 1 by 0 equals to infinity. So here if we try to interpret the results for a type 1 system, for step input application, the result, the steady state error result is 0 for step input, a finite value, okay, a finite value, neither 0 or infinity for ramp input application. Then for parabolic input application, the result is equal to infinity, the steady state error. Okay, this is for type 1 system. So now let us consider a type 2 system. Okay, a type 2 system we will consider. So here we have a type 2 system where the open loop transfer function is given as k into s plus a by s square. Type 2, 2 poles at origin. This is a type 2 system. First we'll determine the position error coefficient for step input application, which is equal to limit s tends to 0 gs, which is equal to limit s tends to 0 k into s plus a by s square s plus b into s plus c. So here when we substitute in the denominator s with 0, the total denominator value will become 0. Sorry, because whatever values there are, when it gets multiplied with 0, the net result will be 0. And when 0 is in the denominator, the result will always be equal to infinity. So Considering a unit step input being applied, the steady state error for step input is equal to 1 by 1 plus Kp, which is equal to 1 by 1 plus infinity, which is equal to 1 by infinity, which is equal to 0. Okay, it is equal to 0. Then we have the velocity error coefficient for ramp input application, which is equal to limit s tends to 0 s gs, which is equal to limit s tends to 0 s multiplied with k into s plus a by s square to s plus b into s plus c. So here again s in the denominator, when we substitute s with 0, then there will be 0 in the denominator which gets multiplied with the other results. So the total denominator value again will be 0. Something by 0 equals to infinity. So kV is equal to infinity. The steady state error because of a unit ramp input, let us consider it is 1 by kV, which is equal to 1 by infinity, which is equal to 0. Okay. Then the acceleration error coefficient K, which is equal to limit s tends to 0 s square gs, limit s tends to 0 s square multiplied with k into s plus a by s square to s plus b into s plus c. S square gets cancelled. So this becomes, when we substitute it with 0, all the s values, it becomes k into 0 plus a, which is equal to a, then 0 plus b, which is equal to b, and 0 plus c, which is equal to c, the denominator. So it is ka by bc. So it is a finite value, a non-zero value. It is not equal to infinity or 0. So here the steady state error because of a unit parabolic input, that gives us 1 by ka, which is equal to this, where k is equal to ka by bc, this will become bc by ka. So here if we try to interpret all the results for type 2 system, in case of application of step input and ramp input, the steady state error values are equal to 0. Only for application of parabolic input we are getting a finite value, bc by ka. For a type 1 system, here in case of application of step input, the result is 0, and in case of application of the parabolic input, the result is equal to infinity. Only we are getting a result, a finite result for application of ramp input. Okay, this bc by ka, here also it is bc by ka. Then for type 0 system, for application of step input only, we are getting a finite result, this. For application of ramp and parabolic inputs, we are getting infinity as results. Okay, so if we try to tabulate these results, okay, if we try to tabulate these results, then we can arrive at a very important conclusion, okay, which will help us to directly reach results without going into the lengthy process. Okay, so here we will list the inputs in one side, okay, step, ramp and parabolic, and here will be the type 0, type 1 and type 2, because mostly you will come across these kind of systems, okay, type 0, type 1 and type 2. So step input and type 0 system, the result is a finite one, 1 by 1 plus kp. Step input type 1 system, the result is 0. step input type 2 system, the result is 0. Okay. Then ramp input type 0 system, the result is equal to infinity. Okay. Type 1 system, the result is 1 by kV, velocity error constant. Then ramp input type 2 system, the result is equal to 0. Then parabolic input type 0 system, result is infinity, the steady state error I am talking about. Then type 1 system and parabolic input, the steady state error is infinity. Then parabolic input type 2 system, the steady state error is equal to 1 by Ka. So if you interpret the results here, for a type 0 system, when these two things come into play, type 0 and step input, in that case we are getting a finite result. When we bring together a type 1 system and ramp input, we are getting a finite result, non-zero result. Then when we bring together a type 2 system and parabolic input, then we are getting a finite result. And in all the remaining cases, it is either infinity or 0 coming as the result. So if you can remember this table, then you can directly arrive at the results. Okay, you can quickly figure out whether the steady state error will be equal to infinity or 0 just by remembering this table. And in case where it is coming one of these three results, okay, combination of step type 0, ramp type 1 and parabolic type 2, there you have to do the calculations. And in all the other cases, suppose you come across a system where it is a, let's say, a type 0 system, okay, it is given a type 0 system and it has been asked that a ramp input is applied. In that case, you don't need to do all the calculations, because if you remember this table, you can directly say that ramp and type 0, it means the result is equal to infinity. Similarly, if something comes up like you see a type 2 system, okay, in the question you see a type 2 system and it is said that a step input is applied. So quickly you will draw this table, type 2 step input, okay, type 2 step input, it means that the steady state error is equal to 0. You don't need to do all the calculations. So here this approach is only applicable for objective type questions, MCQ type questions. There you need to save time, you don't need to unnecessarily do a lot of calculations. So in that case you can use this method, because quickly you can figure out from the options that is given, and just by drawing the table and comparing the type and the input, you can quickly get the result. But in case of subjective type questions where you have to do the step-by-step process, there you should not do this approach. Okay, there you go by the previous methods the way I have done the previous questions. There you have to first write the open loop transfer function, then you have to calculate the error coefficients, whether it is position, velocity, acceleration, and then get the result. Step by step you have to do, because each step carries certain marks. But in case of multiple choice questions, objective type questions, in that case you can, in order to save time, you can use this method, because just by comparing the input type and the number of poles at origin, the type of the system, you can quickly figure out whether the result will be 0, infinity, or any of these non-zero finite values. Okay, so it will save you a lot of time. So here I just wanted to explain or to introduce this concept to you. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.